Good morning, everybody. So, welcome to the last day of the school. Today we have Adi Stern, a professor at the Weizmann Institute in Israel, and he's going to be talking about non-Abelian state of matter, principles, and examples. Adi, welcome.
Thank you very much, Maya. Thanks for inviting me here. Look what a place. As Maya said, I'm going to talk about non-Abelian states of matter, about general principles, and I'll go through those principles using some examples. The outline of the talk has two parts. It's a short advertisement and the rest of the talk. But in case you think this doesn't carry too much information, the rest of the talk will by itself be made of... I'd like to make a few comments about the non-Abelian states of matter, what they are. I know that you heard that from Adam Smith, from Charlie, Marcus, and from Jason, so I'll make that brief. And then I'll go through three examples. The first one will be phase-controlled one-dimensional topological superconductors. You heard quite a bit about one-dimensional topological superconductors, but this will be something which I think you didn't hear. Well, maybe Charlie gave a kind of an introduction or a teaser to my talk. Then in the second example, I'll talk about power fermions and about how we can create them by coupling superconductivity to the fractional quantum Hall effect. And in the third example, I'll talk about non-Abelian fractional quantum Hall state at filling factor 5/2. So that's the general plan. But as promised, I'll start with a short advertisement. So together with some friends and colleagues at Weizmann and around, we prepared an online course called Topological Quantum Matter. The course covers, as you can see on the left, if you can see the letters are kind of small, the course covers all the subjects you have in this school, starting from the quantum Hall effect, covering topological superconductors, insulators, semi-metals, topologically ordered states, experimental tools, everything we could have thought about. And you can find the course either on YouTube or on EDX and Campus IL, which are online teaching platforms. On Google, just search for Topological Quantum Matter Weizmann Online. Anything you make shorter will get you to other places. And there's also an email you can write if you have questions, technical questions or something. So this is my advertisement, and I'd like to encourage you to have a look at that course, in particular if you have questions remaining after this school that you have here. If you don't have questions remaining, then it means we, the teachers, did not do a good job. Okay, so now I'll get to the real part of the talk, and I'll start with this notion of non-Abelian states of matter. What are they? Well, the rule of that game of a non-Abelian state of matter is we need to have a system, usually two-dimensional, but not always, as you know. But anyway, a system where there's an energy gap between the ground state and the continuum of excited states. There's an energy gap which is not a finite size gap. It's a two-energy gap. And there's a degeneracy of the ground state. So there are several ground states of the same energy. Now, the crucial point about non-Abelian states of matter is what I just told you can be written in the following way. There's an Hamiltonian with a block of ground states whose energy I set arbitrarily to zero, and then a continuum of states which, if I diagonalize the Hamiltonian, this is how it's going to look. The upper left block will be all the same energy, namely zero, and all the rest will be many, many other energies. The crucial point is, I'll let you ask in a minute, in a second. The crucial point is, if I now come to the system and change the Hamiltonian a little bit by, changing this parameter or that by gating, putting a magnetic field, anything of this type, as long as the perturbation is weak, the Hamiltonian will change. Of course it will change. But there will be no matrix elements induced between the ground states. So the ground states block will still all be zero. All the rest will change. And when I diagonalize the system again, I'm going to find that the zeros, state zeros, up to an exponentially small correction. And that exponentially small correction can be exponentially small in a in a big size of the system itself. So that's the idea of non-abelian states. We have a ground state degeneracy that's insensitive to parameters. I promised you.
So this ground state manifold, does it need to be, or does it need to have the full symmetry of the Hamiltonian, or can it be a spontaneously broken ground state?
Well, if it's spontaneously broken, then there would be a Goldstone mode, and you get into the issue of you lose the gap. Okay. But you know, this is the strict definition. This is a lawyer's definition. In real life, we can start asking about making compromises. For example, if there is, like in a two-dimensional px plus ipy superconductor, there would be a phase mode that's gapless. Is this the end of the world? Does this, you know, invalidate everything we are talking about here? No, because this phase mode doesn't usually couple to the vortices, which is where we have the degeneracy. Okay. By the way, I should have said it before, but now you reminded me. Feel free to ask questions whenever you want. So that's the idea of non-abelian states. Now, if all the ground states have the same energy, how can you put in dynamics between the ground states? I mean, if the ground states are so stable, how will you put in dynamics? How will you make the system go from one ground state to another? So for that, as you probably know, the key point is to change parameters. So when you look at the system, it has electrons usually in the context we are talking about. It can be other particles, bosons or whatever. But we usually think about electrons. And the ground state wave function is a function of the coordinates of those electrons. And it has parameters. And the parameters, for example, would be the coordinates of quasi-particles. Now, you have a set of degenerate ground states. Sometimes, in many of the instances we're thinking about, that would be exponentially large number of ground states in the number of parameters. For example, in the positions of the quasi-particles, or in the number of quasi-particles. And each one of these wave functions depends parametrically on that set of parameters. Now, when you change those parameters, you change the ground states. And the key point is that if you change these parameters in a cyclic way, namely you start with one set and you come back to the same state, to the same set of parameters, you will change the system from one ground state to another ground state. If you do it adiabatically, if you do it slowly, you will not excite the system. You will change it from one ground state to another ground state. Now that final ground state may be identical to the initial one, or maybe partially identical to the initial one, or maybe orthogonal. But this is how you'll introduce dynamics. You'll change parameters. And by changing parameters, you'll apply a unitary transformation within this subspace of ground states, because you don't excite the system. So you'll apply a unitary transformation within this limited subspace. Now, the crucial point is this unitary transformation is very robust to changes in the way you carry out the change of parameters. So, if you interchange the quasi-particles this way, or with less confidence this way, it's not going to make a difference. The only thing that will matter is the topology of the changes. It's a notion that's easy to think about when you think about physically or spatially interchanging the position of quasi-particles. And this is why that's the example I gave there. But you can extend it also to other situations in parameter space rather than in real space. But you see, the only thing that will matter is the topology. Here you see two interchange with three in a particular way, and then three interchange with one, and then so on and so forth. It's only the topology. So this is a very robust type of dynamics. Now, that led to this amazingly brilliant idea of Alexei Kitaev, that strange time stamp comes out of the fact that he actually wrote the paper in 1997, put it on the archive, and did not submit it anywhere. And then 6 years later, he was kind of forced to publish it. But in any case, what he's saying is that if there's a set of ground states and we can introduce a very robust type of dynamics, that may serve as that may serve us to realize topological type of quantum computation in which we are very insensitive to noise and to decoherence. So that added to the motivation of realizing non-abelian states of matter. But I have to say, the motivation, I think, personally, I think the motivation is there anyway, because this is an amazing, a breathtaking notion. The idea that a system with no symmetries, you know, we know about the generacies in quantum mechanics from day one, from the day of the hydrogen atom. There are all these degeneracies of the atomic shells, but they all come out of rotational symmetry. Here we have a system that has no symmetry. It's full of disorder. It's full of impurity. There are no symmetries other than charge conservation. And even that we're going to give up at some point. And still we have this ground state degeneracy. So this notion is, I think, a very interesting notion. And it brings up the question of, can we actually realize it? Are there states of matter which are non-abelian? And we have several examples. Majorana fermions, which Jason talked about yesterday, and which I'll come back to in a minute, and various quantum Hall states going usually after those names, which we'll get to in my second lecture. Before getting to the Majorana ones, I'd like to say there's a question which I'm very interested in. It's kind of a general question, but and it is, what does it take to have a non-abelian state of matter? What Hamiltonian should I write down? Forget the lab, forget realizing in a lab, but even just realizing at the level of an Hamiltonian, what should an Hamiltonian include to have a non-abelian phase? You know, I know what I need to do in order to get an insulator. I just need a periodic potential and an integer number of field bands. Right, I know what it takes to get a superconductor. I need an attractive interaction between electrons mediated by phonons, and I get a BCS state, and it corresponds to some materials in the lab. What does it take to get a non-abelian state? It's a question I'm very kind of obsessed by, but I don't have a good answer. Anyway, so now I'll switch to the first example I wanted to talk about, and that's the idea of phase-controlled one-dimensional topological superconductor. And in particular, I'd like to emphasize the new setup, which I'll tell you about. But maybe before I start here, are there any questions? Okay, so you know, you can still ask also about the earlier part later. You know, let me say a few words about one-dimensional superconductors. You heard from Charlie, you heard from Jason. But I'll summarize what they told you. What they and I told you now is that one-dimensional topological superconductors are exciting because you have the Majorana zero modes, you can interchange them, then that applies in unitary transformations which are stable, and in principle it can bring you to topological quantum information processing, topological computation. There's a lot of motivation for it. Better still, it's based on a straightforward theory. You saw Jason yesterday, it was so clear. I mean, he basically gave you the entire story on a very small blackboard. It's a quadratic Hamiltonian. We're not doing anything sophisticated. We're using BCS theory, which is really one of the most solid theories in solid-state physics. In Bogoliubov-Dejean equations, the solution is really simple. So the theory is kind of straightforward. But when you look at the experiments, they leave some to be desired, right? No one succeeded in doing braiding, in applying unitary transformations. There are many difficulties in making sure that what we see is what we think we see, and so on and so forth. So you know, what can someone like me do? I'm not an experimentalist, so I cannot improve the experimental situation. I'm not on Twitter, so I cannot use this avenue of activity too. So what I can do, and I think what theorists can do at this stage, is my feeling is we did not yet find the proper experimental setup, the one that makes it easiest to approach the topological phases of superconductors. That's what I'd like to discuss. How can we do that? So you know, the first idea, I think, historically was this idea of a quantum wire proximatized to a superconductor. That was in this beautiful works of Luchin et al. And Yuval Oreg et al. And the idea is you take a wire with a spin-orbit coupling, Rashba spin-orbit coupling, so you have a spectrum of two parabolas which are shifted with respect to one another. You put a Zeeman field which opens an energy gap, and then you have two Fermi points, and if you couple those two Fermi points to a superconductor, you get one-dimensional topological superconductor with two Majorana modes at the two ends. Now, one thing that has to be remembered is, I already said, you need to apply a magnetic field, but also you need to tune your chemical potential to this energy gap. So this idea has two parameters. It has the magnetic field and the chemical potential, and if you tune them correctly, you get one-dimensional topological superconductor. And there are experiments in the last 10 years from various groups. This is some examples starting from the Delft group and Copenhagen group. Weizmann had an experiment. There are many. This is, I think, the most recent one from the Microsoft paper. As you may know, there are 125 authors on that paper. So basically, every line here is an author. It's full of interesting data and various ideas how to make it possible to see the 1D topological superconductivity. Then there's a different direction of mostly by the Princeton group of magnetic atoms on the surface of lead. All those ideas face the same difficulties. The first difficulty is that superconductivity and magnetic fields don't like one another. They are willing to live together, but it looks, like two enemies negotiating. It's an uneasy coexistence. Also, gating and superconductivity don't go that well because it's hard to change the chemical potential of the wire when there are superconductors everywhere around. And disorder is also not helping matters. So we're looking for ways to fight all these difficulties. And the way I'd like to discuss today is by introducing a new knob, which is a superconducting phase. Not the magnitude of the superconducting gap, but the phase. Now, of course, the phase is meaningful only as a relative phase. So we need to have more than one superconductor. So we're going to talk about two geometries. One is this. You see a two-dimensional electronic system, two-dimensional, and on top of which we put two superconductors. In the other one, we put three superconductors. And next year, when we meet, we'll put four superconductors. But before we get into this, let me tell you the rules of the game. We are looking for one-dimensional topological superconductors. So the first thing is we need to identify a one-dimensional system. Here it's going to be this channel, between the two superconductors. This will be a one-dimensional system. We would like to put two Majorana modes at the two ends. What we are going to do, first step, in order to put those two Majorana modes, is what seems to be totally nonsensical. We're going to put periodic boundary conditions. So then the system has no ends, and there won't be any Majoranas at the two ends, right? So why is this a good thing to do? Because once we put in periodic boundary conditions, identifying this point and this point, or identifying this side and this side, once we do that, the system has a momentum in the x direction. X is along the 1D. The momentum in the x direction is a good quantum number. And what we need to do is to look at kx equals 0. Now, we need to solve for the spectrum of the system as a function of this kx and look at kx equals 0. And what Kitaev found when he discussed topological superconductors in one dimension is that if you find at kx equals 0 a single gap closing point. What do I mean by that? Well, you'll see it in a plot next slide. But a single gap closing point. So there should be only two states coming to 0. One from negative energy, one from positive energy. You know, it's the group of the Hamiltonian. It's always symmetric with respect to 0. So two energies coming to 0. If there are only two coming, then on one side of that gap closing point, the system will be topological. On the other one, it will be trivial. Which side is which is not, we'll worry about that later. But this will be a topological phase transition. So this will get us to what we want. And then, you know, come with scissors and cut the periodic boundary condition that you put, open it to an open system, and you'll see Majorana modes at the two ends. So theoretically, it's easier to think about a system with periodic boundary conditions. And therefore, that's what we will do. Now, one thing that should be obvious from what I told you is that we need to break spin symmetry. Because if we have a spin symmetry, we will always have two states coming together, because there will be a degeneracy. Each state will be doubly degenerate because of spin. And there will be two states coming together, and that's not a topological phase transition. So we'll need to break spin symmetry, and as you know, we usually do it with spin-orbit coupling. Not always, but we'll talk about that. How do you recognize a 1D topological superconductor? You see, I'm saying at the theoretical level, because experimentally it's way, way harder than theoretically. So you, as I said, you focus on kx equals 0, you solve the Bogoliubov-Dejean equation, you change some parameter, you look for such a gap closing point. If there are two of them, that's not working. That's not a topological phase transition. You need to have one. Okay, so the first geometry, as I told you, will have two superconductors, and this is the one you see here. So we have a two-dimensional electronic system with spin-orbit coupling. We have two superconductors with a phase difference of phi. I think later it changes to theta, but at the moment it will be called phi. And we'd like to make this channel between the two superconductors a one-dimensional topological superconductor. Now, you see, it is one-dimensional. It has spin-orbit coupling here in the 2-DEG. It has superconductivity, and it has a magnetic field. There will be a magnetic field applied parallel to the channel. So it has all the ingredients of the one-dimensional system, but it has also a phase difference. And what I'm going to argue is that this phase difference is going to replace, by and large, it's going to replace the chemical potential as a parameter in our phase diagram. So instead of looking at things as a function of chemical potential and magnetic field, we will look at them as a function of magnetic field and phase difference. And later on, when I make this into three superconductors, we will have a phase diagram as a function of two phase differences, and the magnetic field will be pushed out of the system. There won't be any magnetic field. Yes?
Does the direction of the magnetic field matter?
The direction of magnetic field? Yes, definitely.
Okay.
It should be parallel. Now, you can be non-parallel in two directions, obviously, either going out of the plane or in the plane, but not parallel to the channel. Each one of them is bad in its own way. Okay. Other questions? Okay. So what are we going to see in this system? There will be two features which I'm going to mention. One is that there will be a robust topological phase that will require very little fine-tuning, and this will happen when the two sides when the phase difference is close to pi. In principle, you will need no magnetic field. In practice, that's too ideal. Anyway, that's the first thing I'd like to point out to you. And the second thing is actually quite interesting. This system, usually, how do we get a system to become topological? We play with parameters until we get to a topological phase transition. We close our eyes, cross the topological phase transition, and when we land on the other side, we have a topological system. Here we're going to have a slightly different way, which is the system will tune itself into a topological phase. It's always good that someone else does the job. The system will tune itself into a topological phase through a first-order transition. So I'll explain that in a minute. So first, let me expand on those two things. First, the issue of the robust topological phase. So what I'm going to tell you is that, I'm going to show to you, is that there will be a phase diagram, as I said, with the phase difference on one axis and the magnetic field on the other axis. This is in contrast to the wire that had a chemical potential on one axis and a magnetic field on the other. So now we replace the chemical potential here by a phase difference, and in principle we make this point, the extreme far left point of the topological phase at zero magnetic field, as you see here. Now there are assumptions. So what we see, you can ask, but what is the dependence on the chemical potential? And the answer is there is very weak dependence of this phase diagram on the chemical potential. Basically changes the chemical potential, stretches or distretches, whatever the word is, those diamonds on the x-axis. There are assumptions here. Spin orbit energy should be large and the superconductors should be wide. I won't get into too many details. In any case, this is the first thing. This is the phase diagram. Second thing is, as I said, it's the topological phase, the first order phase transition into topological phase, and the idea is this. Let's take our system with the two superconductors and not tune their phase. When you have a Josephson junction, this is Josephson junction. When you have a Josephson junction, you can tune the phase by connecting it to a flux loop or by driving a current, or you can just not tune the phase. If you don't tune the phase, the system will find the phase that minimizes its energy. Now we put a parallel magnetic field. So we broke time reversal symmetry, and that phase that minimizes the energy of the system is not necessarily constrained to be at zero or at pi. In practice, what happens is at weak magnetic field, this is the phase that minimizes the energy. At zero magnetic field, it's zero. As you change the magnetic field, at some point there's a phase transition, a first order phase transition, in which the system jumps from a value very close to zero to a value very close to pi. So as you change the parallel magnetic field, the system will go through a first order phase transition, which will land it in terms of the phase diagram, will land it into the topological phase. So the system will become topological in a first order way. Now, excuse me, I suddenly remembered that there's also time to keep. And actually, having remembered that, I'll just tell you that you can see this first order phase transition on the critical current of the junction, and maybe it's something that was seen in an experiment of Amir Yacobi. I won't get into the details, but if you look at how the critical current looks as a function of parallel field, you see that it has this non-monotonic structure, which is consistent at least with the first order transition that I mentioned. Anyway, how do we get to this picture? How do we get to this phase diagram and to this entire story? So you remember, the system has two DEG with a spin-orbit coupling and a parallel magnetic field. Two DEG with spin-orbit coupling, with Rashba spin-orbit coupling, has this Fermi surface that is two concentric circles. Basically, you take the parabola, as you put in spin-orbit coupling, you shift, like in 1D, you shift the two parabolas with respect to one another, but since it's in 2D, you do this, you make it into body of evolution. And what you get are I don't know how to call it, but two concentric two-dimensional parabolas or whatever, and the phase, the Fermi surfaces look like that. You apply a parallel field, what you do is you shift the two Fermi surfaces with respect to one another, and you're supposed to shift them only slightly or exaggerated for you to see the effect. Then you put in the two superconductors in, and you make phase difference of phi. Now, what's the spectrum? What we need to do, as I told you, is to solve for the spectrum for kx equals 0. So once you fix kx to be 0, you have only the y direction, the direction perpendicular to the channel, to worry about, right? So basically, in that direction, what you have is a particle in a box problem, but the walls of the box are superconductors rather than insulators, right? So we need to solve the Bogoliubov-Dejean equation with of a particle in a box, square box, let's say, with the two walls of the box, a superconductor with some order parameter delta and a phase of plus phi over 2 or minus phi over 2. So we need to solve that problem and find this single band crossing that we talked about. That is in some sense, the easy part of the problem. This will tell us when we have a topological phasor and when we don't. Of course, then we go to the experimentalists, and they also want to know what's the gap, just to see if it's smaller or larger than temperature and so on. So for that, we need to solve for all kx's. But I probably will not discuss that here. So anyway, as we said, kx equals 0, we need to find a single gap closing. And here's our particle in a box problem. Superconductor, and this is the box. Yes?
That's okay. So quickly, I know you said this, but you need the magnetic field to open up a gap, right?
You will see why I need a magnetic field. I'm coming to
okay, but so I'm just wondering if you put a perpendicular field, won't that also open up a gap? Okay, I'll leave that question.
Perpendicular field is in some sense a game changer because it makes the phase depend on position. It makes it makes kx not being a good quantum number. Okay, so a particle in a box problem comes in physics thinking together with a Bose-Sommerfeld condition, right? How do you know to quantize the spectrum in a box? You calculate the phase that a particle accumulates as it goes back and forth and equate it to an integer number of 2 pi's. So here's the condition. The phase that the particle accumulates as it goes from one superconductor to another and then back has 4 parts. And I'll tell you what the 4 parts are in a minute, but we need to sum them all up and get 2 pi times an integer. So the 4 parts, the 4 terms are divided into 2 types. 2 terms are those which you accumulate as you propagate, and they include the PDX, the momentum times position. That's proportional, of course, to the distance you carry out as you go back and forth, 2 times W. And it includes also a Zeeman phase, which we'll have to see why we need it. So those are the 2 parts you accumulate as you move. There are also parts that you accumulate by just banging your head on the wall and being reflected back. And there are 2 parts to this. One is phi, the phase difference, and the other one comes out of making sure that the wave functions glue together in the right way. So this other one is 2 inverse cosine or arc cosine of the energy divided by delta. And I don't know how to derive this on a board in like 5 minutes. You just need to do it. So in any case, we need to look at this Bose-Sommerfeld condition and solve it and solve the energy from it. And we're looking for zero energy solutions. It's easiest to take the case of W being very small, and then this equation becomes slightly simpler and tells us that the energy of a state is delta, the superconducting gap, multiplied by cosine of phi over 2 plus or minus the phase accumulated by the Zeeman field. So let's see how this looks. If I look at the energy of that state as a function of the phase difference, you see it's a cosine. Now let's imagine that I have no Zeeman field. Okay, so Bx is 0. Then I have delta times cosine of phi over 2, and this plus minus indicates that I have two of them. I have two states coming from above to 0 and two states coming from below to 0. That's not a single gap closing, that's a double gap closing. So that's not a topological phase transition. This is, by the way, this point. The point, because phi should be pi in order for that to be 0. So this is this point, and it takes you from a trivial region to a trivial region. It doesn't take you to a topological region. If you want a topological region, you need to turn this Zeeman field on, and then what it does, it separates the two states from one another. So now you have a single gap closing and another single gap closing, and you open up a topological region. And you see it here. You turn on the magnetic field, this axis is the magnetic field, and you open up a topological region. Now, the magnetic field is part of this phase that's accumulated, Zeeman phase that's accumulated as you go back and forth. So this phase is the Zeeman field multiplied, the Zeeman energy multiplied by the time it takes to go back and forth, and that time depends on the Fermi velocity, and that Fermi velocity depends on the chemical potential. Depends on the chemical potential. So this is where the dependence on the chemical potential comes in, but it's kind of weak. I should say, in everything I said, we thought about the magnetic field as creating only a Zeeman term, because in two dimensions, if you put a parallel field, there's no Lorentz force. Now, that's Jason had yesterday this distinction between the world he lives in and the real world. So that's the world, the world of theories. In real life, 2 dimensions are not 2 dimensions. There's some width, and therefore there is an effect to the parallel field. I mean, there are many difficulties that come in that I'm kind of sweeping under the rug, but still. Yes?
But if the energy is as large as the gap, why is there, so there's still no tunneling into the junction? Everything is perfectly reflected.
There is tunneling in the sense that the wave function decays exponentially, but there is no normal reflection. So this is clearly, when I say there's there's an ideal world and what's being neglected, it's this normal reflection. What happens if there is a normal reflection? Here you see the phase diagram. There are topological regions, there are trivial regions, and you see the solid lines look like kind of diamonds. And they touch the magnetic field equals 0 point here at pi. Now that is in the absence of normal reflection, and the way that comes out of the equations is you linearize the spectrum. So delta should be much smaller than E Fermi. If you take the next order in delta over E Fermi into account, you see you replace the solid line by the dashed line. So the diamond is not really a diamond, the lines are slightly bended. Okay? So that's the phase diagram that we find, and that's for periodic boundary conditions. If you open the boundary conditions, then, just a second, I'll just finish the sentence. So if you open the boundary conditions, you're out of analytical calculations, at least for this problem, and you need to solve the problem numerically, and I'll let you enjoy the colors while we listen to the question.
Yeah, so it's insensitive to chemical potential, I guess, at a global level, but how sensitive is it to variations in chemical potential?
Variation, that's actually a very good question. Variations that are slow we can live with them. What do I mean by that? If you are somewhere at the center of the diamond, then and you change the chemical potential a little bit, you shift the diamond a little bit, or you stretch it and compress it a little bit. If you are deep inside, that's not going to affect you. So slow changes in the chemical potential are far less of a problem here as compared to the wires. So you can say, well, that should have an effect on disorder, on what happens. That should lead to a different dependence on disorder. And to that I will say, just wait.
And by slow you mean slow in space, like varying over long?
Yes.
But and if you would have like a Gaussian distribution of chemical potential, I guess there's a disorder strength at which the whole thing doesn't work, right?
Yeah, okay, so that's what I said. Wait a few minutes and we'll get to disorder.
Thank you.
Okay. What happens with disorder is kind of surprising. At least it was to me. So anyway, for open boundary conditions, what you see here is this is the solution of this is fixed at some magnetic field, and what you see, this is as a function of energy and phase difference. It's the local tunneling density of states in the bulk and at the edge. And you see at the edge, at zero energy, in some range of phases, you see a peak, and that's the Majorana state. Okay? Now, that's something that can be done experimentally. And Charlie's Copenhagen group had the first experiment a while ago, and now they have a second experiment. And Amir Yacobi's group also had an experiment, and I have no time. And there's also a slightly different experiment in Delft by Srijit Goswami. But I'm going to cut short, and I'll, try to make myself feel better on doing that by thinking that Charlie explained it before I came here, and I hope that's right. And the reason I'm doing that is two reasons. One is I want to tell you about the three superconductors setup, and the other is I promised the disorder issue, and I should keep my promises. So this is a very recent work that I did with Omri Lesser, who is a graduate student at Weizmann, a very good graduate student at Weizmann, and Yuval Orego is my colleague. And what we did was the idea is we are going to eliminate the magnetic field completely out of the problem. And we're going to have three superconductors. So there's, those are the two superconductors we had before. You remember I warned you that phi will change into theta. I noticed it only while speaking, so I'm sorry for that. We now have theta and minus theta, and the central one will be phi. So that's going to be the setup, but there will be a fine print. There will be a condition that you need to satisfy. We will need to have two different velocities of the two spin branches in the two superconductors. So in particular, in this superconductor, in the central superconductor. So there will be two different spin branches, of course, and they should have different velocities. Now, that's not happening in the Rashba story. In the Rashba story, you take, in Rashba spin-orbit coupling, you take two parabolas, you shift them rigidly with respect to one another, so the Fermi velocities stay the same. We will need to go beyond this Rashba. And once we do that, we'll find single gap closing at kx equals 0, and that's what will give us the topological phase. Yeah.
Is the reason that we need to do different velocities and spin branches kind of to emulate the Zeeman? Or
in some sense, someone must do the job because we eliminate the Zeeman, and they will do that. The way that will happen, you will see. They together with the third superconductor will do that. Yes, again.
So if you have two Majoranas, where will they sit?
In between. So the wave functions, the wave function of the Majoranas will be split between those two normal regions, and you'll see in a minute what I mean.
So it should be smaller?
Yes, in the precise sense is the key issue now. We need to in everything we do, we need to separate the two spin branches from one another because we don't want spin symmetry. And there are several ways to do that, and they refer to different works. So you can separate the different spin branches by making helical states on the two sides of a 2D topological insulator. And we'll do something similar to that when we talk about parafermions, but that's going to be only in the third lecture. You can separate in momentum space, as we said. That's the Oregluchin way. This is the Fourier-Kane way. You can separate in energy and spin polarize the entire system. And that's the Kitaev model that you talked about, that Jason talked about yesterday. What we're going to do is we're going to separate the two spin branches in velocities. That story is what I just told you. If we have two of them, and if the phase difference is pi, which means here theta is pi plus or minus pi over 2, if the phase difference is pi, the gap closes. That's what we'd like to use. So if the phase difference between this and this is pi, the gap closes. Now, in this geometry, if there's no parallel field, what we saw is, yes, the gap closes, but it double closes. We need to separate the two closings. So now we put the third superconductor, okay, with an order parameter that looks like delta prime e to the I phi. The difference between delta and delta prime is of no significance, but the difference between phi and theta is going to be significant because now we have two phase differences. So we'll have a phase diagram with the two phase differences on the two axes. Now, how wide should this superconductor be? Well, if it's infinitely thin, then clearly it makes no difference. You can forget about it. In contrast, if it's very, very wide, like think of it as 100 meters wide, then you just have two Josephson junctions which do not know from one another at all. So in the first case, if the superconductor is very thin, the phase difference for closing the gap should be pi between these two banks. If it's very, very wide, the phase difference should be pi between these two banks or between these two banks, right? Because you have two junctions that do not know from one another. So the key idea is, well, maybe for the key idea, what do I mean when I say very, very thin or very wide? I should say it compared to something. And clearly the thing to compare to is the coherence length. It's the superconducting coherence length because this is the length at which the wave function decays in the third superconductor. So it's the coherence length in the third superconductor. So we have two distinct behaviors in the case where the superconductor is thinner than its own coherence length or broader, wider, fatter than its own coherence length. What we want to do then is to have it very thin for one spin branch and very wide for the other spin branch. Then the gap closing points for the two spin branches will be different from one another. So what we need is a coherence length to be different for the two branches. Now the coherence length is Planck's constant multiplied by the Fermi velocity divided by delta prime. Planck's constant is not negotiable. It's not going to be different for the two spin directions. Delta prime is the same delta prime for both, at least if you don't take some sophisticated superconductivity, which we don't. Then the thing that can change between the two spin branches is the Fermi velocity. And this is why we need different Fermi velocities. Now, so we need a spin-dependent Fermi velocity. Once we have that, we can solve we can solve this, or maybe I should say we can solve this spectrum of this system for kx equals 0, and we find that the gap closes when cosine theta plus cosine phi, plus cosine phi multiplied by the hyperbolic tangent of ws, this width, divided by psi is 0. Now, what we want is this hyperbolic tangent to be very, very small for one spin direction, and 1, which is what happens to hyperbolic tangent when the argument is very large, for the other spin direction. And when that happens, we have in a phase diagram of the two phase differences a topological region, and of course it's periodic. It's a phase diagram of two phases, so it's periodic. And I should say, that's a side comment, we can now make these regions, the normal regions, as narrow as we want, because before we needed W to be reasonably large for the Zeeman effect to have its action as you go back and forth, but now there is no Zeeman effect, so the normal parts can be as narrow as we want, essentially. So that's a setup for a topological superconductivity that has no magnetic field at all and no dependence, or very weak dependence on chemical potential. Now it turns out, if you ask yourself, if you look at the meaning of this equation, you find that if you put theta and phi on a circle, because they are phases, so this is theta and minus theta, and this is phi. If you want this condition to be satisfied, you need theta and phi to form a triangle that includes the origin. So it includes, so that they basically form a vortex. You need that. Now, how shall we get different Fermi velocities for the two branches? So, in some sense, first of all, I'm going to discuss this for like 2-3 minutes. I want to say it's in some sense easy. There are lots of materials when that happens naturally. There are many materials where that happens naturally. We looked at mercury telluride and at various TMDs. So it may come out of the material properties. It may come out of proximity, if you're in a heterostructure, proximity to a second subband, or it may come out of having a periodic potential in the x direction. In fact, Omri, together with a few collaborators, found this in an earlier work, and what we are doing now is to see that it's part, the example they showed is part of a very general principle. At the theoretical level, the question of unequal Fermi velocity is the philosophical question of presumption of innocence or presumption of guilt. If you ask, what do I need to do for the two Fermi velocities of the two spin branches to be different, the answer is, why do you think they should be equal? When there's no spin symmetry, they'll be generally different. What we're looking for are ways to make them very different. There are a few things that can be said about that, but I won't go over them. I basically told you the headlines. What I'd like to do in my remaining 5 minutes is, as promised before, to talk about the effect of disorder. And the reason I like to do that is I want to say that while disorder for a wire is clearly an enemy, disorder in this setup may have a friendly effect. 3 minutes? Great. Let me start by just showing this. This is numerical calculation of, you saw the geometry. This is the two superconductors geometry. One superconductor, the other superconductor, parallel field, phase difference. So the first setup I discussed. And what we look at, we look at 4 points in the topological phase and ask, how localized are the Majorana modes close to the ends? How well localized are they as we turn on disorder? Now, of course, the more localized they are, the better off we are, because then they don't talk to one another. So we'd like to localize them as much as possible. So you see, we turn disorder on, and you see what happens at the different 4 points. You identify them by the colors. But let's look at the black one, because it's the easiest to see. You turn disorder on. This is disorder. And this is the localization length of the Majorana. And you see that the Majorana becomes more localized as you turn on the disorder. So disorder helps localizing the end modes. Why is this in 2 minutes? Well, we need to identify who's responsible for that, and it's the gap at large k. It's no, so far we talked only at k about kx equals 0, but in fact here it's the gap at large k, because what determines kx equals 0 determines the binary question of are you topological or trivial. If you are topological, there will be Majorana end modes. How localized they are, this is determined by the spectrum at large k. Okay, it turns out the gap at large k enjoys having some disorder. It gets bigger as you turn disorder on. Here you see the spectrum as a function of k, calculated numerically for some value of phase difference and Zeeman field. And you see that at kx equals 0, the gap is reasonably large. We are far from the transition. But then at kx equals kf, it turns out, the gap is minimized. Now, why is this? The physics is quite simple. If this is our one-dimensional channel, and this is a superconductor, this is a superconductor, if you are at large kx, you mostly move parallel to the channel. So you're not going to experience the superconductor much. And you need the superconductor in order to be gapped. So in contrast, if you move with a small momentum in this direction, you'll go a zigzag between the two superconductors, and you'll feel the superconductor much more. So this is why the gap here is pretty large, and the gap here is quite small. Those two minimum points are the 2 kf's. I won't get into details. I'll just tell you that what happens with disorder makes the gap at kx equals 0 go down, and makes the gap at large k go up. And the reason is that at small kx, the system is in some sense a p-wave superconductor. This is why all this topological stuff works. But at large kx, the system is more like an S-wave superconductor. And in an S-wave superconductor, superconductivity is protected by the Anderson theorem. And that is essentially what happens here. So I won't get into that. I'll just summarize this part by saying, I listed the difficulties before, which I think are the difficulty of why is it so difficult to see these damn one-dimensional topological superconductors. It's because of this uneasy existence of superconductivity and magnetic field, uneasy coexistence of gating and superconductivity and disorder. I think that, as I told you, I think that we need to look for new novel setups. There are several suggestions, there probably will be more. I told you about 2, but my guess is you can come up with more. And the ones I told you about, the idea is to replace the magnetic field by tuning of phases, to get rid of the dependence on chemical potential, and then the effect of disorder is weakened and sometimes becomes even friendly. So I gave you a very short answer to the question. I promised more. But the crucial point is disorder makes the Majorana modes more localized in the setup of 2 superconductors. It's a legitimate question, what happens in the 3 superconductors? And the answer is only chronological. We didn't do it yet, but we are doing it. So I think I'll stop here, and in the next hour I'll talk about power fermions in about 5 hours. Thank you.
Is there
Yeah, there was. Yeah.
In one slide, you said that I think proximity to a second subband could also cause these different velocities. I didn't really understand it. Could you elaborate a bit on it?
Yeah, I happen to have a few slides. Yes. So, you know, this is a 2-DEG with spin-orbit coupling and a potential, a confining potential in the z direction. We usually don't think of that. We say 2D and that's it. But there's a confining potential in the z direction, and the shape of the confining potential quantizes the spectrum in the z direction, the subbands, and also affect the spin-orbit coupling. Now, we need the spin-orbit coupling to depend on this direction. And if that happens, the difference between the wave function of the lowest subband and the first subband, which are just particles in the box in the z direction, this difference makes the effect of spin orbit be enhanced when you are close to the to this point. You see here the spectrum as a function of k for the two spin branches in two different colors, and you see that the Fermi velocity here, if you are close to this point and if you are close to this point, the Fermi velocity is very different for this point and for this point. It's hard for me to point out exactly that. One is pretty shallow and the other one is quite sharp. Right. And those are two different velocities. So, the blue one and the red one at about -1, energy equal to -1, have these very different slopes. Those are the two very different velocities. But the key point is we need the spin orbit coupling constant to depend on z.
Thank you.
So, if there are no questions, please do it during the coffee break or lunchtime. And we thank you again.
Thank you. Thank you.